In this lecture, we're going to talk about matchings, and specifically we're going to talk about the maximum matching problem. We already know how to solve the matching problem, and we already know how to solve it efficiently. We can show that the constraint matrix in the integer program is totally unimodular. The reason we're talking about it is because there is some special purpose algorithm for matchings that happens to be very insightful. So the maximum matching problem, we're given as input a graph. That's the only input. The objective is to find some set of edges m so that m is maximized, the cardinality of m is maximized, and no two edges share a vertex. This second property is the property of a matching. In a matching, no two edges share a vertex. Here we have a particular instance, a particular graph, and we can find a matching inside of this graph. We'll make the matching edges in blue. Here we see that when we have the matching, these blue edges, no two edges share the same vertex. And we can actually show that the matching that we just put in blue is a maximum matching. If we were to add any edge to this matching, then two edges would share the same vertex. The first thing we'd like to talk about with respect to matchings is upper bounds, or dual bounds. So we're going to be drawing on ideas that we were talking about a few weeks ago: primal bounds, upper bounds, and optimality. Let's suppose that we have some matching M, and we also have some cover C. We can show that the cardinality of our matching is at most the cardinality of our cover. Showing this is a relatively straightforward proof. Every edge in M has to be covered by C. That means that for every edge that we have in M, there is at least one vertex in C. That's because for every edge in M, no two edges share the same vertex. Here we have two examples of matchings and covers. In this case, we have a bipartite graph, which we'll introduce in just a little bit. Our matching is in blue and our cover is in pink, or fuchsia. We can see that every edge of the matching is adjacent to one vertex in the cover. On the other side, we again have a matching. In this case, the maximum matching has exactly one edge. Every other edge would touch this edge. And our cover has two vertices. In this case, every edge of our matching also touches the vertex of our cover because it has to, but there's also an extra vertex here in the cover that doesn't touch an edge of our matching. In this case, the size of our matching is strictly less than the size of our maximum cover, or minimum cover. And in the other case, our maximum matching meets the size of our cover. The next idea we'd like to introduce is that of an augmenting path. An augmenting path is going to be a path, and we're going to describe this path by a set of edges. An augmenting path has effectively four properties. The first is that every odd indexed edge is going to be a non-matching edge. That's going to be an edge not in the matching. Every even indexed edge is going to be an edge that is in the matching. Additionally, the first and end nodes of this path are both going to be exposed nodes. The first node is going to be the first node of the first edge, and the last node is going to be the last node of the last edge, the kth edge. We're going to call these nodes V0 and Vk. By exposed, we mean that both of these nodes, V0 and Vk, are not adjacent to any edge of our matching M. Finally, the number of edges in our augmenting path, P, is going to be odd. So K is going to be some odd number. Here we have an example of an augmenting path. The path P is in fuchsia. We'll note that a couple of the properties. First, the odd indexed edges are non-matching edges. That is, they aren't in the matching colored in blue. All the even indexed edges are matching edges. The first node, V0, and the final node, V5, are both exposed nodes. That is, both of these nodes don't touch any edge in the matching. Finally, the number of edges in this path is odd. We have 5 edges, and so that's an odd number. Hence, the path P in fuchsia is an augmenting path. The reason we're interested in augmenting paths is because they allow us to improve matchings. If we have some matching M and some augmenting path P, then we can construct a new matching M prime. This new matching M prime is constructed by taking all of the edges that are in both M and P and subtracting out the edges that are in both M and P. This new matching M prime is going to have at least one more edge than our original matching M. So in this way, by combining M with an augmenting path P, we construct a new and better matching. Here we have an example of a matching M and an augmenting path for this matching P. From this, we can construct our new matching M prime. We'll construct the matching M prime in this other graph. First, we look at all the edges that are in both M and P, or rather all the edges that are in M or P, but not in both. That includes this edge. It includes this edge. It includes this edge. And it includes this edge. Note that the other edges that are included in both M and P, here and here, aren't included in our matching M prime. Also note how the augmenting path actually helps us improve. It lets us alternate the edges of M with the non-matching edges, and instead we include the non-matching edges in our augmenting path in our new matching M prime. Finally, note that our new matching M prime has one more edge than our original matching M. In this case, our matching M has 3 edges, and our matching M prime has 4 edges. In addition to helping us improve matchings, augmenting paths also allow us to prove a condition of optimality. We can say that if there is no augmenting path with respect to a matching M, then M is going to be an optimal matching. It's going to be a maximum cardinality matching. We're going to prove this claim by contradiction. So for the sake of contradiction, suppose we have some matching M prime that's not equal to M, and this new matching M prime is an optimal one. We're going to consider the graph constructed by taking all the edges of both M and M prime and subtracting out the edges that are in both M and M prime. This is similar to the operation we use for augmenting paths. Here we have an example. The matching edges M are in blue, and the matching edges M prime are in green. For the sake of counterexample, the matching M prime has more edges than the matching M. We've also highlighted in fuchsia the edges of our graph G. The edges of our graph G consist of all the edges that are in both M or M prime, but not in both. We can notice a few things about this graph, not just our example, but in general. All nodes in this graph have degree at most 0, 1, or 2. That's because every node is touching at most 2 edges, one edge from the matching M and one edge from the matching M prime. Because these are the degrees of all the nodes in this graph consists only of cycles and paths. We note that if there is a cycle in this graph, then it has the same number of edges in M and M prime. We can see that in the example down here. But more generally, a cycle is going to consist of edges that alternate between M and M prime. The same is true of any path of even length. A path of even length has to be constructed of edges that alternate between M and M prime. Finally, because M prime has at least one more edge in it than M, there must be at least one path with one more edge in M prime. That's because these even paths and these cycles all cancel each other out with respect to the cardinalities. They take an even number of edges, the same number of edges away from M prime as M. So there must be one remaining edge that's going to create a path with one more edge in M prime. It turns out that this path is going to be an augmenting path. In this case, it's going to be an augmenting path with respect to the matching M. It's going to be a matching with an augmenting path because it's going to alternate between edges of M and not M. Every other edge is included in M prime, which is a non-matching edge for M. It's also going to have an odd number. It won't be an even length path because the even length paths have the same number of edges. This is that odd length path. And finally, both endpoints of this path are going to be exposed. That's because they're edges of M prime and not M. Here we have an example of the augmenting path we found inside of G. This now proves the claim. If we have some matching M, and it has no augmenting path, then it has to be optimal. If it wasn't the case that M was optimal, then there would be some other optimal matching, and by contradiction, this other matching implies that there's an augmenting path, but we assume that there was no augmenting path, so the contradiction is complete.